Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
This is actually the last talk we're having in this room, as next week we'll be doing the talks over in the new building 99. So join us over there. Today I'm going to ask, first of all, please turn off your cell phones. And not just on vibrate, but turn them totally off, because it interferes with the film and the sound with people watching online. Thank you. Today, John Nordlinger of Microsoft Research is going to introduce our speaker, Will Wright. John.
Hello. So I'm very excited to introduce Will Wright. As you know, Will Wright, like many of us, has been heads down producing code. The upcoming game Spore hopefully won't slip anymore due to our request for Will to come and speak, but we're certainly very appreciative. Will Wright's one of the most famous game designers in the world. He's actually created a genre of gaming around consumer simulations, beginning with SimCity and with the world's most popular selling game, The Sims. And if you haven't heard, he's also working on what's likely to become the next most popular game. First he did it with Sims, then he did it with Sims 2, and then it's likely to be Spore. And he's just a maven in this industry. He's known for clutching up some of the most talented PhD students in the world, and then later on we find out they're working at Maxis and EA. And he's been shaking up the world in gaming and simulations and academia for a long time. So please welcome Will Wright.
Let's see, can everybody hear me? Yes. Is this loud enough? Yes. Okay. So I'm going to talk for a while, and you can ask questions for a while, but feel free to interrupt me in the middle and ask questions while I'm talking, because I'd rather be kind of more interactive. If you feel comfortable raising your hand or just yelling out, hey, stop. So they said I could talk about whatever I wanted to, so I decided to go a little bit on the abstract side. I'm going to talk about emergence, dynamics, design. Just about everything I've learned about emergence, I've learned from three sources. Playing Go, the game, playing with cellular automata, which when I first got into computers just became a major obsession of mine, and ants. And I'm guessing since you all work at Microsoft, you probably get a lot about computers here, but not a lot about ants. So I'm going to go a little ant heavy on this talk, so you'll at least be exposed to a little bit of myrmecology that otherwise you might not normally get. Now, emergence really is kind of the concept of how can we take simple systems and use those to build complex things. And, you know, I use that in a lot of ways in my work. You know, the simulations I build are very much based around very simple rule sets combined to give very complex behavior. In game design, really a nice aesthetic for game design, and one of the reasons I like Go so much is that I think that if you can give a player very simple, understandable rules and have a very interesting emergent strategy from the game, that's a really good aesthetic for game design. And I think Go exemplifies that very well. And lastly, I found that emergence has been very important in the way we think about player communities. This is a recent game between Utah versus the Andorians, which is kind of sad that I know what they're called. But you know, we're finding more and more when we design games, it's about how we cultivate a player community around that game. And it turns out it's very much an emergent phenomena where very simple processes between these players and what they do and the content that they create and move between them become very fundamental aspects of the complexity that eventually emerges as a player community. We also see that these rules work very well for mirroring physical systems. So I think there are some underlying aspects of the player, and the player experiences it as a possibility space. You know, these are all the possible things that can happen to you in the game. Now, over time, we've tried to build games with larger and larger possibility spaces, and we've had to attack that with larger and larger teams, especially on the content side. And so, more recently, I'm trying to think, like with a game like Spore, how we go back and throw less data at the problem and throw more procedural algorithms at the problem. In other words, lean more heavily into the idea of emergence so that we can build a larger possibility space for the player with less people on the team. Now, just a few terms. I tend to think of things in terms of structure, which is kind of like the static layout and organization of something, and then dynamics basically as little parts that I stick together to build more complex systems, you know, and build models, which in some sense these models are in the game, but they're also models in the player's imagination that the player's building as they play the game. In some senses, it's kind of the reverse process of science, where you're actually looking at a lot of data and trying to reduce that data to the simplest possible rule set. We're kind of going the other way with games. We're trying to take a simple rule set and have it, basically explode out into a large amount of possibilities. In some senses, it's kind of been a trend over a long period of time. It used to be that we tried to describe the physical world through calculus, very complex equations. More recently, we're kind of going for simpler solutions using simulation. In some sense, calculus is a very linear process. Simulation is a much more parallel process, but using simpler components. And this has some very kind of light analogy almost to education in the way we tend to learn. Story and gameplay have a similar kind of yin and yang to them. Story is a very linear process of learning. Gameplay is very parallel. Try a lot of different possibilities and then add them up to build, kind of that model. But they're both model building technologies. Story and gameplay, I think, are evolutionary technologies that we've developed to build models of the world around us. Now, as a just simple example, if you were using kind of old math to say how much of this field is covered by these crops, you would probably go in and figure out the area calculation for the rectangles in the circle and subtract them at the union areas, whatever. But there'd be a long kind of little equation that you would plug in numbers to figure it out. Using the more simple parallel simulation approach, you'd basically throw darts at this thing. And after some number of darts you've thrown, you would count how many of the darts landed inside the crops and how many didn't, and basically come up with a land area approximation from that. And this is just kind of a simple example of the difference between kind of the old way of building models of the world mathematically and kind of the new computational ways. That's called the Monte Carlo technique for obvious reasons. Now, in design, I spent a lot of time with interns and team members exploring dynamic space. And what I mean by that is that we're taking simple rule systems, putting them together, and then studying the system. We interact with it, we play it. What does it look like? Is it fun? Is it interesting? In some sense, these prototypes become just kind of little recon units that we drop in random spots in the dynamic space of all the possible dynamic systems we could build. And then we do hill climbing, kind of from those points. And, most of the time, they're fairly uninteresting areas of this space. Every now and then, we trip over a really interesting area of rule sets. So it's not so much a process of engineering as it is a process of discovery. Because it, is emergent, it's inherently really hard to kind of predict what rule sets will add to what behavior. So it's really more about how can you efficiently explore the rule space for these systems. Having said that, as I've played with these systems a lot, I've found that time and time again I keep seeing the same patterns and things over and over that I see in very different simulations, very different settings, across communities, simulations, and game design that have, for me, over time, as a designer, become kind of my little parts, my Legos that I put together to build these systems. I want to kind of give you my view of this, the way I think of it. We'll start with topologies, which is when I'm looking at the nouns of a system. It might be players in a community, it might be elements in a game. They typically fall into one of these three categories: agents, networks, and layers. Acting on those structures, we have dynamics. These are the ways in which those structures can change over time. And these are some of the most common kind of dynamic rules I found that I've used to recombine as my Legos, my toolkit. Lastly, there are basically the languages through which you build these systems. What I call paradigms. These are different ways of looking at the world and modeling it. They're roughly in chronological order from cybernetics up to network theory. As we've used computers to start building models of the world, how do we basically put a grid over the world and decompose it? So I'm going to dive into this a little bit on the topology side. Now, in some sense, the topologies in the system kind of represent the nouns. These are the things that we're actually modeling. The dynamics represent the verbs. These are the actions, that are occurring on the nouns. And the paradigms really become the grammar. This is the language we're using to kind of build these systems. There's no real set order in which we explore these systems. There's a lot of kind of give and take, back up, go left, go right. A lot of orthogonal kind of processing going on in exploring these systems. But I'm going to start with topology a little bit. In games, there are a lot of different ways you can apply topology to games. Just the overall game flow. Some games are very linear, story-driven. Other ones are branching, like Choose Your Own Adventure. Other ones are kind of more gated systems, like this one in the bottom left corner. Is something like Quake, where you have kind of an open-ended level, but at the end of the level there's a red door with a key, and if you don't find the key, you're not going to get to that door, but then you open it into another area of relative freedom before you go back to another gate. Games like SimCity, more open-ended simulation games, are more like a web in the upper right here. There's kind of some large space of phase space that you're exploring in the game. Now, there's kind of organized here from rigid to flexible in terms of the way these things relate to each other. The agents can be very flexible in terms of how they end up kind of connecting and interrelating. The layers tend to be fixed topologies, more like landscapes, where your neighbor is always your neighbor and always will be your neighbor. In a game like SimCity, the agents can be layers of crime and pollution. With ants, and here's where the ants start coming into the talk, they have the same kind of things in terms of the topology of the way they're built. The dynamics are acting upon these topologies over time. Now, propagation is the first one I'm going to talk about a little bit. And this is propagating something through a system. It can either be material, information, or even just a pattern that's kind of moving through some system. Frequently, these patterns move through networks, and networks are kind of developed for the propagation of information or material. There's usually some medium through which this is propagating, and it's through some period of time. Now, like in fan communities, one of the really interesting things that we've looked at over the years is the way certain things propagate through fan communities. Kind of one of the common things in game design is that you want to target the hardcore gamer. Over time, if you can target the hardcore gamer effectively, then they will start telling their friends and family and whatever, and you start propagating outward toward more and more casual players. And there's an amplitude change as you start moving out. And there are a lot of things you can do to kind of control or promote this propagation. A lot of things happen with like cheat codes. The very first cheat code I put in a game was just really for my own use, but then I found, this is the original SimCity, that some people were going on the net saying, hey, does anybody know what the cheat code is? And other people would go on the net and say, oh yeah, I know it's this. And it became a form of social currency. And what was interesting is it became a reason for people to go on the net, connect with other players to get the cheat code, and then they would keep talking. And then at some point they'd say, oh, you should see my city, I'll upload it. Oh, that's cool. And actual communities would form because the propagation of that information was looking for a medium to propagate through, and people would meet on the net. And this is before the internet. This is like old, like little game bulletin board systems. But I started realizing the power of using information propagation and scarcity to actually grow player communities, because then they are forced to look for a medium through which to propagate, this information, and then they end up connecting and using it for totally different purposes after that. We see that with every game, even with like exploits. So this is The Sims Online. Somebody found an exploit where they could make their sim burst into flames on command, with this weird combination of things. And it was interesting, at first a few players figured this exploit and they were telling their friends, but about 3 weeks later, the people were having like these self-immolation parties, in the game. And it was just really interesting to study the speed at which it propagated. There's also a thing in epidemiology about the contagion period of a disease, which is interesting, that depending on a lot of factors, if you take a disease and let's say you're contagious for 1 week, you might infect 10% of the population. If you increase that contagion period to let's say 2 weeks, you might end up infecting maybe 50% of the population, 5 times as many, even though you've only doubled the contagious period, because of the compound interest, basically. What we found with certain games is that if you can keep people playing a game for 2 weeks instead of 1 week, that they will actually end up propagating it to a much wider group of people that will end up playing the game. Just because they played it twice as long, they'll end up propagating it to maybe 5 times more people. And so, that's where expansion packs and things come into play very heavily. So a game like The Sims, somebody will play for a few weeks, put it away, they'll go buy an expansion pack, pull it off the shelf, play it a few more weeks, and effectively we're using them as a marketing tool because they're playing the game longer. Now, ants are very good at propagating information. You probably all know about pheromone trails. The technical, actual word is anal communication, which is what they call it. Ants drop these pheromone trails that they use to propagate information, which controls, the colony. Now, one of the things I want to stop and just talk about a little bit here is why I think ants are so cool. Ants are, one of the most intelligent things that we can study through deconstruction. The intelligence of an ant colony is amazingly high, almost as smart as a dog in a lot of problem-solving environments. But the individual ants are incredibly stupid. And we can very much deconstruct the way they work. They're very simple little state machines. And so we can actually, at every level, kind of understand the way these simple little kind of state machine behaviors lead to very complex, elaborate intelligence. And so that's why I want to focus a little bit on ants, because I think there are a lot of lessons here that you can use, both in systems architecture and, game design and community design. Now, we've all seen ant trails and the way ants drop little things when they find food. Their antennae actually are very sensitive noses. And so they're actually walking through a little pheromone tube, and as they're walking down, they're actually continually going left and right, turning back toward the strongest point of the scent. When an ant discovers food, it actually drops a very simple little trail, goes back to the nest with the food. As that trail gets stronger, more ants follow the trail, and so it's self-reinforcing. The ants that don't follow the trail, their trails evaporate over time. So this is a system that's very efficient at network routing, and they've done a lot of problem-solving things with ants, trying to figure out, how efficient this is, and it is amazingly efficient. Ants have other pheromones, like inside of them, that are alarm pheromones. If you crush an ant or an ant gets killed in combat, these alarm pheromones are released, and then it signals the other ants to go kind of into attack mode. If it's above a certain strength, they'll actually just attack anything near them. If it's below that strength, they'll be attracted to it. So it actually pulls in other ants in the surrounding area, and once they get into the middle of the area, then they go into attack mode. I did a game quite a while back called SimAnt, where it was actually based upon the behavior of ants and the pheromone trails that they would drop. And it was actually very heavily based on the work of Edward O. Wilson, who's like the premier myrmecologist. And it was very interesting how robust of a system we were able to build using just simple pheromone trails and the way the ants were dropping it and how it influenced their behavior. In fact, The Sims, and so The Sims really at that level is based upon ant pheromones. All the objects in the environment, as well as people, are continually advertising across several pheromones. And the other Sims are responding to those pheromones and being pulled around. So that means the environment can change very dynamically. I can design any kind of house or kitchen, and the Sims will basically respond appropriately based upon the environment informing them, what they should do when. Growth is the next dynamic I want to talk about a little bit. Growth, in most natural systems has this kind of inherent tipping point thing, this kind of characteristic S-curve, where people are turning their lights on the highway at night. At first it's a few cars, a few more cars. There's some point at which when you see most of the cars on the road, or over half of them have their headlights on, you turn yours on. So there's a very fast tipping point that occurs in that system, and that's true of a lot of natural systems as well. You can look at anything like resource usage, population growth, whatever, and you get these characteristic curves. This whole idea of the singularity that's coming is kind of based around what happens when these curves hit an exponential. But they never go asymptotic. They always kind of come back down to, declining returns like this. We can get these through simulation using very, very simple techniques. In this little grid, I basically have a rule which is, for every cell, pick a random neighbor and try to add another one nearby. And then if you look at the growth of that block, it actually gets a curve like that. Using a very simple modification of that rule, if I just say pick a random spot, and then if it's empty, add a new cell, you get a very different curve. And so we can use very simple, this is kind of like the Monte Carlo technique, very simple little rules to actually generate these curves that we use for simulation. Ants' growth are actually very interesting and elaborate. Initially they're up flying around mating in the mating phase, and what happens, the queen is impregnated, a new queen lands, and lays her first batch of eggs, her first brood. From that brood, she basically has to support the colony for the first 2 to 3 weeks. And they go out and forage, bring a little bit of food back, and she's actually able to, make a few more eggs. And that first 2 weeks, she's actually surviving off of body fat the entire time. Over time, as the colony grows, the other ants start bringing back large amounts of food. Then the growth of the colony really takes off. And so if you look at the curve of an ant colony, the population growth, it's very much that S-curve. And then at some point, the queen starts generating new male ants, and they go through the breeding cycle again. And so most natural systems have some sort of a growth pattern like this, where there's basically kind of a bootstrapping process, then there's the really steep part of the curve, and then there's some end game involved. The colonies themselves, as well as they're grown, have very specific times which certain parts of the colony nest are made for certain purposes. We'll go into that a little bit deeper. Grouping is the next dynamic I want to talk about a little bit. Now it's interesting, in most systems that I've studied, grouping is a form of cooperation that's driven by competition. In other words, grouping is not necessarily altruistic, but things are coming together to give basically a competitive advantage against other groups. It's dependent on economies of scale, in that 5 things will work better than 2 individual groups of 2. And it's also enabled by communication and control, and encourages specialization. So there are things that when you have systems that start grouping, other dynamics grow out of that naturally. We're kind of familiar with the idea of grouping similar items together for various reasons. A lot of times in games, you'll group together units of similar type and now treat them as one unit. And so it's a form of player abstraction, where the player can kind of jump up a level and say, okay, I'm going to put my archers here, my phalanx there, this there. And so for the player, they're actually able to operate at a higher level of abstraction. A lot of times we have things that are grouped that are very, identical or similar. Other times we have groupings of very dissimilar specialized components. And this is where grouping eventually will lead to specialization over time, whether it be a city and all the different kind of functions in a city, or a cell. In ants, ants go through this very specific kind of development process, from egg to larva to pupa before they're born. There's actually quite a bit of management involved in an ant colony, taking care and raising these things and feeding them properly, because depending on how they're fed, they will actually be raised in different castes, different roles in the ant colony. And there's a huge number of eggs being born by the queen that all have to be kind of sorted into various piles, fed the right type of thing to develop into specific castes depending on what the colony needs at a given point in time. One of the interesting problems that ants have solved very emergently is how to sort larvae. Each larva stage puts out a particular smell that the ant can detect. If an ant is randomly walking around and encounters a larva, and it doesn't smell that smell in its particular area, in other words, it smells kind of standing out relative to the area around it, it'll pick it up and just walk around randomly. And it'll carry it around randomly until it comes to an area that's high in that smell, at which point it'll drop it. Time using just this random motion and that simple rule, ants very effectively will sort their larval broods. And then they'll actually bring them to specific chambers and give them, the right things to raise them into certain castes. The next dynamic we'll talk about is order or priority, basically how you allocate something in a sequence. In a lot of games, it's very much, do I shoot the flank saucer first or these guys first? The order in which the player approaches problem solving becomes very critical to how, whether they can solve it or not. One of the interesting kind of ant examples for me is the army ant, which is a migratory ant. It's nomadic. It actually takes its entire colony, picks it up, and moves it about once every month. They make these rivers of ants that are guarded by soldiers, as you see kind of on the edge here. And they actually have to pick up all the larvae, the queen, and everything, and move this entire, several million ant colony across the forest floor. What they tend to do is they will make a new nest. Once they've made that nest, they'll stay there for about a month. And then they hormonally will sequence their foraging patterns. And so they'll one day go off in a very specific direction, forage that area, eat all the food over there, and the next day go off 120 degrees or so out of that first one. And every day they do a very efficient exploration of all the food sources around that nest. And then, after they've done that, they pick up the whole colony, move it again, and repeat the same process. And this is all controlled through pheromones within the ant colony. Allocation is really about player allocating resources. Ants deal with allocation things in a really interesting way. Ants have two stomachs. They have a private stomach and a social stomach called a crop. Ants do this really cool thing called trophallaxis. When two ants come up and meet frequently, they will tap antenna, and then one ant will regurgitate what's in its social stomach to the other ant, and it'll eat it up. And they're sharing food all the time. This, first of all, equalizes the food supply, so these few ants that have eaten a lot share their food with all the other ants very effectively. But more importantly, what this ends up being is a form of global communication. It's a global bulletin board system. For instance, the queen puts out a very specific trace chemical all the time. And then whenever she's doing trophallaxis with another ant, they're getting a trace of that chemical. And as it does trophallaxis with another ant, it spreads through the entire colony very fast. Now, if the queen should die, that chemical will dry up in a few days, and every ant in the colony knows that they do not have a queen because they don't have that trace chemical anymore. And that's just one example. They also use that for understanding what food sources they need more of. If they need more protein or more water, every ant has basically a global record of what all the other ants are eating. And so in some sense, ants are using pheromones not just in a local, communication scale, but in a global scale as well. So it's the balance actually between kind of this global bulletin board system through trophallaxis and the local pheromone trails that they're dropping that become the basis of their intelligence. And a lot of scale-free networks have this same property. If you study the internet, you have kind of, higher-level global nodes that are controlling propagation through a lot of lower ones that are more peer-to-peer-like. And that balance is actually very interesting. Now, just by the way, this is probably the one useful thing you'll get from this talk. If you really want to kill ants, what you do is you buy these things, but you don't use them the way they tell you to use them. You don't just put down the steak. What you actually have to do is get a toothpick, get it kind of wet, and mix it in the middle of the ant steak. And then take the poison out of the ant steak and put it right along an ant trail, but only once you have a really dense ant trail. And you have to wait until the ant trail gets really dense, put down a lot of this poison over about a 1 hour period, and within 1 day, guarantee that colony will be dead. And this actually makes use of trophallaxis because all you have to do is poison about 10% of the ants with enough poison so that they spread it to the other 100%. And then it's a fatal dose for everybody. So it's kind of critical that you get that 10%, the highest possible dose, in the shortest possible time. So don't use them the way the package tells you to. Mapping is about temporary associations. Sometimes networks, sometimes it's mapping of performance or through state machines. One of my favorite games from all time is this game called Battlefield 42. Have any of y'all played this game? Basically, it's this game where you can kind of go run around, shoot other people, but they have all these cool vehicles. You can jump into a tank or a jeep or even a battleship. They have all these cool things. And it's interesting to watch the way different players kind of play this. The Jeep turns out to be the funnest, coolest vehicle in the game because it's so fast and maneuverable, and people have found a lot of cool exploits. But it's interesting to watch different players approach this game because for a given situation, every player kind of has their favorite vehicle or weapon that they choose. And it's very much a mapping endeavor. People think of that in terms of the game, like, oh, I'm going to face this enemy, I need that thing. And for them, the mapping is the game. in a different situation, they'll choose different things, but every player has kind of their own unique individual mapping here. One of my favorite levels in Battlefield 42 was this one where there's this big bowl where the enemies would respawn, and I could actually get a Jeep and like run over the guys as they respawned in that spot. And but the bowl, it felt very much like skating, so it was kind of like this weird combination of Grand Theft Pro Skater 42, where you're like basically running over people, but you're like in a skate park, and then it's in this World War II environment, and it was like such a cool mixture of things. In communities, a lot of what goes on in online games is mapping between players. Players kind of discovering each other, and that becomes the basis for really thriving communities, is if they have an effective way to discover other players that are either doing what they're doing or support their play style or the structures they're building. It might be a guild in a game. It might be a fan site that somebody's building and trying to get other people to come on the fan site and do specific stuff on the fan site. Ants, as I said before, are fairly simple state machines to some degree. I mean, they're actually fairly high processing, but an ant is roughly equivalent to like an old, Macintosh or something in terms of its overall processing neural ability. In some sense, you can kind of look at ants pretty obvious. In certain environmental situations, they pick very certain behavioral responses, and you can see that pretty clearly through ant experiments. Now, you all know that ants have these basically specialized roles. You have the queen, soldiers, workers, and occasionally male drones that are the only males that are born, and they only live for a couple weeks, so they're mostly female. Specialization, one thing about this is it's enabled by communication. That as soon as you have a way for units to communicate and then group together in the grouping dynamic, it encourages specialization because they can compete more effectively. It was actually the evolution of the neural cell, of neural systems, that allowed multicellular organisms to start building specialized organs and such. And that's when life achieved a much higher level of complexity through that specialization. It tends to breed networks. So once you have these things, there's kind of a self-supporting thing between specialization, breeding networks, and leaning on networks. They're very self-supporting. City are specialized according to different functions, but also your time of day, if you think about it. You specialize your time of day according to different functions as well. And then you rely very heavily upon the networks, like in this case the roads, to move through those different areas of specialization. Games have endless examples of these things, from tech trees to goal states. Fan communities as well. We've seen that as fan communities grow, they start falling into very different roles as they specialize in those roles, and they have very specific kind of networks through which they communicate. And different players, will communicate through entirely different networks depending on what they're doing. One of my favorite types of ants is the leafcutter ant. These guys basically go around. They cut leaves very efficiently with these very sharp little mandibles, as big as they can carry, and then carry them back to the nest. They're also called parasol ants because they look like they're kind of these little parasols above them. What's interesting is they bring all these leaves back to their nest, but they don't eat the leaves at all. What they actually do is they chop up the leaves into a mulch and grow a fungus on them, and that's what they eat. So they're actually farmers. And they're one of the most interesting ant species because of the degrees of specialization that they've achieved, because the endeavor they're engaged in is actually quite complex when you look at kind of all the different roles they have to fill. This is what a typical leafcutter nest looks like. That large thing in the middle is basically the fungus garden down in that chamber. The other holes are like little, basically waste holes where they take all the waste, from the colony. It might be dead ants or decayed leaves or whatever. They've undug some of these nests, and they're just huge things. They're up to 60 meters wide, 20 meters deep. What happens is you have this whole cast of ants that do nothing but go out and cut leaves. Other ones that they give to the carriers that actually bring it back to the nest. The carriers drop it through holes in the top of the nest, these little pieces of leaves they've cut off. And in that section of the nest, a few inches below the surface, are some smaller workers that then take the leaves and cut them up a little bit smaller, and they fall through smaller holes. So the nest is like this kind of successive filter. And at every level, and there might be up to like 6 or 7 levels, there's a smaller cast of ant that lives at that layer and cuts the leaf into a smaller and smaller piece. And so the pieces are slowly being chopped up in finer and finer pieces by all these different workers. Then the very tiniest little parts of leaves fall down into this main chamber into a big mulch pile, where they're actually growing fungus, and a totally different cast of ant is managing the fungus and churning the leaves and tending the garden the whole time, and then bringing that food to other workers. There are yet other casts that are doing nothing but helping the queen lay her eggs. Other ones that are nursemaid ants that are actually raising larvae at different stages and feeding them the right things. Still others that are actually just basically cleanup workers, the garbage men, that are cleaning stuff out of the nest and out of the food pile. And these ants actually are forbidden from entering the rest of the main nest. If they try to enter the rest of the main nest, they're killed by the other ants because they don't want to infect it. And so they actually have amazingly elaborate roles, just like a human city. A lot of ants, have various worker castes. A small number. Leafcutters actually have something like 20 or so unique castes of ants, different sizes. These are all born the exact same. So they all came out of the queen as the same egg, and they were raised differently with different food allotments as larvae that would actually turn them into these different castes. Ants are just wonderful examples of specialization, through the different species. These are honeypot ants that have a special caste called repletes that are just living food containers. Their abdomen distends. They get fed this very sweet, sugary stuff by the other ants, and they basically can sustain the ants through droughts and stuff as large storage containers. They never move. They stay up there all the time, and that's all they are, is basically their long-term food storage. This is the Malaysian suicide bomber ant, which is really cool. This is probably the first suicide bomber on the Earth. They have muscles in their abdomen that can contract so tightly that the abdomen actually explodes, releasing poison over a fairly large area. And if this ant species gets attacked, these ants will run into the middle of the battle and explode themselves, killing the enemy ants. And they've evolved this behavior. I should point out, one of the things that Edward Wilson was studying ants for, one of the questions he was really trying to answer was, why do they always act so altruistically? The kind of short answer to that is that when all ants are born, they actually, because of the particulars of their genetics, they share 80% of the genome with all their sisters in the colony. So they share so much of the genome that from the gene's point of view, it's very much in its favor for an ant to sacrifice itself to save the queen or other reproductive members of the species, which kind of plays into Dawkins' idea of the selfish gene. Ants also domesticate other insects, which is really bizarre. These are aphids, which are managed by certain ants on plants, where the ants protect them, actually are critical to the aphid survival, reproduction, and everything. So the aphids actually extract this little kind of honey out of their abdomen that the ants eat. Basically that's the output of the aphids eating the plant that they're on. And so ants actually herd and maintain these things as domesticated insects, and that's all they can eat. And if the aphids were to go away, the ants would die. Other ants actually are slave-making ants, where they don't have the ability of the castes to feed their queen and do all the things they do. What they do is they run into another colony, kill off their queen, replace their queen with the slave-making queen, and basically trick the ants into raising them instead of their original queen. And they do this through a lot of what they call pheromone propaganda. They will actually mimic the pheromones of the host ant species. These are poison-spraying formica ants that can shoot fairly large, long-range poison streams at each other. These are weaver ants, which actually build their nests out of leaves by pulling them together and weaving them into colonies, and they live in the trees in South America. And the process I don't have time to tell the process, but it's an amazing process through which they manage to pull a group of leaves together, weave it up into one colony, and then build a colony inside these things. So ants are probably one of the best examples from nature of how grouping of these individuals that really are identical right off the bat has led to specialization and given them a huge competitive advantage. One of the interesting statistics is that imagine how many people are on the Earth, 6 billion or so. Imagine how much they all weigh together collectively. Now imagine how many ants it takes to equal one person. And the collective weight of all the ants on Earth way outweighs the collective weight of all the people. Just to give you kind of some sense of how successful they've been. Now, nesting is kind of the last dynamic I want to talk about, and this is where true emergence really happens. When you start taking all these other dynamics of specialization, grouping, networks, communication together, you start seeing organization and behavior at radically different scales, and this is where systems start exhibiting much larger ranges of behavior than the simple systems underneath them would kind of imply. Typically, in a lot of systems I've studied, what happens is that you have agents competing at some level, and these might be single-cell organisms competing, they might be small startups competing in an economic sense, or individuals competing in some economic sense. What happens is that over time, some of the communication system will start forming between some of these agents, and because of that, groups will start forming, and this is the grouping process. Now, as a group, these can specialize and actually outcompete the individual agents. So there's this balance, this very fine balance between cooperation and competition, where the cooperation is being driven by the competition with a larger set of agents. And over time, what happens is the other agents start collectively assigning into groups so they can effectively compete And now competition starts at this level as well. Now these organized groups are now competing with each other. They find that by grouping together, communicating in a higher level entity, they can now outcompete the other ones around them. And so what you ended up is this set of nested systems driven by this balance of cooperation and competition. I mean, think about it, like in some sense you're all competing with your coworkers for your job, job levels, job promotions, but at the same time you're competing or cooperating within the company. And the company is competing with these other companies. But every now and then several companies will get together, form an association to outcompete some other company. And so a lot of the complexity that we see around us, in nature, in environmental, economic systems, etc., are driven by this same kind of set of processes. Within the system, we have the individual agents at each level. Some are collective, assemblages of other agents. We have networks, kind of between these things where they're communicating. And we also have layers, of which the emergence is actually kind of bubbling up through. A lot of games can be seen the same way. This is like in real life. In a game sense, something like Grand Theft Auto, you have a physics engine at the very low level, how the cars move, things interact. Then you have very simple little AI for the people and very simple little physics models for the vehicles. On top of that, you start building things like missions and situations. And then there's a story arc kind of laid on top of the whole thing. So in some sense, you have the same type of emergence happening kind of at a design level in a game like Grand Theft Auto or The Sims. Just to kind of recap here, so when you have individual agents competing, there's growth within the system. That drives grouping, which involves control structures and boundaries around the group, what is in the group, what's not in the group, which then drives specialization within the group. That involves propagation of information, network building, etc. Then there's allocation decisions going through that propagation, mapping decisions on the network, and then there's a nesting, which is the level jump to the next level of competition. So that is kind of one of the more interesting general principles I've seen kind of across player communities, game design, simulation design. There are other aspects of dynamics that I'm not really going to cover today, but that become kind of part of the toolkit of the designer when you're kind of building systems like this. Last thing I want to talk about really quickly is paradigms, which is kind of like the language through which you can kind of deconstruct the world into these simple rules and build these models. Now, these are really ways of capturing the world, and each one's different, and none of them are really the world. They're all just representations of the world in different systems. As an example, you have relativity theory, which does a great job of explaining the universe on kind of very large scales. It's very, very accurate. We have quantum mechanics, which does a wonderful job of explaining, the essence of nature and physics on a very, very small scale. But they're mutually incompatible. They just don't talk to each other at all. They each describe their area of reality very well, but in this case, neither one of them can describe a duck at all, okay? Which is really like the interesting part of reality, where these dynamic systems exist. So they obviously, interesting current technology is the way you interpret the future or reality. In futurism, when the first cars were really being sold in large numbers after the war, they were saying that we would have these giant things, which it turned out they were right. We have SUVs and nobody's driving, it appears, But this is kind of the view of the future back in the 50s. And we had atomic power, of course, and so we assumed, of course, we're going to have nuclear-powered airplanes. This is actually a Ford Auto, the Nucleon, that they were planning on building, and they were nice enough to put the nuclear reactor, way in the back. Then in the 60s, chemistry was going to solve all of our problems. This is from a musical, DuPont's Wonderful World of Chemistry. Then, when the space program was in full swing, the Apollo program in the 60s, 2001 came out, and they were extrapolating just 40 years in the future. Well, actually, it was less than that. It was more like 30 years in the future. And they were assuming that within 30 years, we'd have these giant lunar colonies and space stations in orbit and all that. So they were, we always tend to kind of over-extrapolate where we are. Today it's more like network dystopia. Tends to be, the dystopian futures that we predict. Kind of going back to around World War II, one of the first kind of paradigms for simulation was cybernetics. And this is very much kind of based on natural systems and observing the way they have goal-seeking behavior. Basically positive or negative feedback can be built into a control system. And this is what you build things like autopilots and thermostats out of. They found that by chaining these things together, they could actually get much more elaborate behaviors. And a lot of analog electronics, analog computers were actually based upon this idea of chained together cybernetic systems. And some of the very first models, ballistic models and stuff, were built in these very elaborate, very hard to program. I mean, you think digital programming is hard. Trying to program one of these analog computers, because any little error would propagate itself through the network. After that, in the 50s, as we started getting more digital computers online, this guy Jay Forster kind of came up with this idea of system dynamics. And in system dynamics, everything is either basically a stock or a flow. stock is like something you can measure, like population or money. A flow is something like birth rate or tax rate. And using that, you can model almost anything. It's almost based upon really a chemical model of the way everything works. That you have pipes and then you have storage units, so things flowing through it. What's interesting is that people try to apply this to all sorts of stuff. This is actually a model that somebody built on their psychic awareness. If you actually look at the things here, it's like trueness of mind and prayer intensity, and this is their system dynamics model of their, I think, their religious beliefs. This is actually a run out from his model on how high his prayer quality was rising, based upon various things. You can take any one of these paradigms and apply it to anything, but that doesn't mean it's correct. They used system dynamics back in the early 60s. There was a very famous book called Limits to Growth, which was predicting that the world human system, basically our economic system, would collapse around 1987. And they built a model of food production and population growth and economics and all this stuff. And it turned out it didn't happen at all. They got a few variables a little bit off. And by being just a little bit off on things like the increase in agricultural productivity because of herbicides, their model, 20 years out was useless. I mean, it was nowhere near reality. And that actually brought up the first evidence of what we later understood to be chaos theory, which I'll get to in a second. Also, kind of way back, surprisingly way back, cellular automata was invented, which is the idea that you have very simple little simulations using very simple little rules that lead to elaborate behavior. This is Conway's Life that probably most of you have seen. Von Neumann actually kind of came up with this, and these are the systems that actually exhibited some of the first true emergence in a computational form. SimCity, in fact, in some sense, is very heavily based upon the idea of cellular automata. We have CAs at the local level in SimCity calculating things like land value, population, and crime. Very, very simple rules, but the propagation and interaction of these layers is very complex, the way it kind of works. On top of that, we actually have a system dynamics level, which is at a high level figuring out how many people are moving into the city and stuff like that. So in some sense, SimCity really is kind of combining cellular automata with system dynamics, and it's a hybrid model between those two things. It exhibits the same kind of thing that the ant colony is doing, where you have global versus local structure and communication. And the balance between those two actually ends up being critical to kind of the complexity of the system. As I was mentioning before, as they were studying the system dynamics models and some of these other models, they were finding that they were useless at predicting things like the weather or economic or social systems very far out. And that led to kind of an awareness of chaos theory, which is very simply that, if you take a system and look at the result of it over time, and then you go back to the beginning of the system and move it just a little bit, the initial starting configuration, with certain types of systems, the result can be wildly different with just a very slight change in the initial configuration. There are other systems that are actually the opposite, where no matter where you start, you're going to end up at the same place. Those are very stable systems. But most of the really interesting natural systems tend to be chaotic, which puts inherent limits on kind of what we can predict. But chaos theory did have a lot to contribute in terms of visualizing phase space. There are a lot of interesting kind of ways at looking at all the different dimensions of a system and the way in which you can understand it over time. We actually end up using a lot of this in game design. This is actually a phase space graph of 1,000 players, how they played The Sims, across certain dimensions of gameplay. And so we're actually able to capture metrics of players playing a game and get a sense of where the crowd goes, where they fan out, where different player types tend to kind of congregate over time just by looking at representations of the phase space. In some sense, what we're looking at for a lot of these systems is this interesting balance between disorder and order. That's where chaotic systems really strike this interesting balance. And most of the really interesting systems that we discover, nature, economies, etc., tend to fall in that middle range there. That's where the highest complexity really ends up. Now, they were really going in chaos theory initially for a general theory of complex systems, and it failed in that regard, but it came out as a very good descriptor of the different systems out there, and which ones are complex systems, which ones aren't, and why. Kind of from that idea, from chaos theory, came the idea of complex adaptive systems, which are the systems that are focused within that range. And these are systems that, again, span most of the interesting things that we want to simulate. But these are systems that are, in some sense, self-aware. Looking at complex adaptive systems, they're not just these elaborate mechanisms, of gears, but in fact, they're much more like biology. They have a lot of feedback cycles. One of the interesting ideas that actually came from biology and entered into this is the idea of an adaptive landscape. And this is a view of evolution where you can see this landscape here is actually a fitness landscape. And any organism is a particular spot on that landscape. Every spot on that landscape is actually a different genome. And the height of that landscape is how fit that genome is. So that means that every organism, when they're born on a spot, they never move, but their offspring are slightly displaced. The ones that are uphill will reproduce a little bit more effectively, therefore they're more fit. And therefore you get these moving clouds. Evolution, the process of evolution, are species clouds moving across this landscape. In some sense, another kind of way of looking at this is in gameplay terms. When a player is playing a game, they're moving through some game space, and there's a success landscape where certain areas are the goal states represented by peaks. The player's trying to climb those peaks. There are different paths to get up there. They might find a sloping, easy path up to the top of the peak, or they might hit a cliff where it's impossible to go that way and have to back up to some other part of the system. In The Sims also, we use this a lot. I talked about how we used pheromones as the model for The Sims behavior. The way that actually added up was that we were building what we called a happiness landscape that was invisible to the player, but the Sims could read. At any given time, this Sim in the middle here is hungry. He's really hungry, a little bit lonely, a little bit bored. But based upon that, it generates a unique happiness landscape, which says that the thing that gives him hunger has the highest value to his happiness. So in other words, what direction can he go in this landscape to fill his happiness the most effectively? And it's toward the fridge. When he goes and he eats, happiness now drops. Hunger now drops. And now lonely is the most important motive for him to fill, at which point it reevaluates the landscape that he's climbing. And now, so he's continually doing a process of hill climbing here to basically raise his happiness. Now that he's not lonely, he's bored. And now the pinball machine is advertising playful. So in some sense, the Sims are continually exhibiting this hill climbing process across a happiness landscape, which is very much kind of inspired by ants and adaptive landscapes. The gameplay landscape in The Sims, and this is kind of from the player's view, is we wanted them to understand that you could kind of go in a material direction or a social direction. To get the highest success in the game, you really had to balance the two of them. If you didn't, you were stuck at one of these local maxima on the far left or right. So really, it's a game of bowling. We were trying to get it right down the alley and not fall into one of those gutters. Network theory is the last one I want to talk about, and this is kind of the more recent theory. In studying things like the internet and a lot of network systems, they found some really very simple but powerful ideas. The idea of power law distributions, that in almost any complex system, you have a few nodes that are very highly connected, but most of them have very low numbers of connections with a very characteristic kind of curve. This is true of a lot of systems across a lot of different ways of looking at it. This is a social network on The Sims Online. And we saw the exact same kind of result in almost any social network that you look at an online game. You get this power law distribution. You find out one of the things that's interesting is that weak links in the social system tend to be the really important ones because they bind together different groups. And that's why these kind of large nodes, whether it be a Google or a really popular person in an online game, are the ones that are bridging all these other sites together. We found this, down at a very tactical level in The Sims Online. We had a mafia develop kind of emergently in the game, where we had this woman who became the boss, and she had this very elaborate kind of organization of capos and bosses underneath her that exhibited the same thing. In fact, this is like how she was recruiting people into her mafia. They had little pay scales and everything. Now, basically, I'm going to kind of wrap up here just with a little bit on design. So basically, we have the idea of simple rules leading to very complex systems that we can use across simulation game design community. As a designer, you always kind of have to think about all the different aspects of what you're designing. For any design artifact, there are, a large number of kind of criteria that you can measure that design against. In some sense, you can take those criteria and decompose them into categories and a hierarchy. A game or a piece of software is no different. The designer's job really is to balance all these different things continually. And as you're exploring design, you're actually kind of going down this branching tree of all the possible designs that you could make. So at the end of the tree are all the different millions of designs that you could end up with. One of those is going to be where you're going to end up, depending on the path you take down this tree. Traveling down that tree is going to involve a lot of backtracking. And also a lot of how can I look far down that branch without committing to it, without spending a lot of resources. And this is where you do a lot of prototyping and stuff. So using these dynamics, basically I see as tools for kind of navigating my way through design trees like that. And, players, when they play a game, they understand kind of the language of the game. Who am I? What am I doing? What are the verbs that I have accessible to me in a game? And a lot of that you can actually uncover by the stories they tell each other. Designers have their own language, So what I'm talking about today with the dynamics is really more the design language. It's not something that I expect a player to understand, but it's something a designer that I communicate to other designers through that language. At the end of the day, what you really want is the player to be able to build a very simple model of what they're interacting with. Over time, have them slowly bootstrap the complexity of that model up in their head very smoothly and enjoyably. Because at the end of the day, the real model that we're trying to build in these things is in the player's head. That's where all this stuff is actually happening. The computer is just kind of a compiler for that mental model that we want the player to be building. So I'm going to stop talking now. And I think we have a few minutes for questions. Yeah.
This command is one of my favorite simulations of all time.
Oh, thank you.
And so much more is known now, and you may even know more now. Are you contemplating a sequel given today's knowledge and technology?
I would love to do it. You know, as a designer, it's like you always want to kind of go on to new things. You know, I think I could probably do a really good version of SimAnt compared to what it was. The technology was so primitive back when we first made SimAnt. But yeah, I'm not going to say no. But there's so many other things I would rather do. I think, you know. Yeah.
You're mentioning the model in the player's head. Something that I've recently been reading about is the idea of MMO players finding rules in the game that aren't there and becoming very stubbornly attached to them. I'm curious if you have any experience with that with Sims and other complex games of that sort.
Yeah, we had a name for that at some point. I think we called it delusional simulation. But I had players that played SimCity. They would tell me, like, oh, I was playing SimCity and this plane crashed in the nuclear reactor and it caused a surge on the power grid and this fire popped out over here. And they were describing this long chain of causality that did not exist. I knew because I designed the simulator, but they were convinced, you know, the simulator had all these moving parts, and they had seen, you know, humans are amazingly good at taking a random sequence of events and finding some plausible causal chain for how they're related, and we make heavy use of that, actually. Once I kind of tripped over that, I started realizing that there's a lot you can do with ambiguity. You know, basically, if there are things that we have a hard time simulating, we actually have two processors available to us. We have the computer processor, and we have this processor. And so we ended up offloading a lot of stuff to this processor when we found out that it was so effective at doing that. You know, in The Sims, for instance, when the Sims go up and talk, they speak in this kind of gibberish language. You know, in fact, if you actually put real dialogue in English in there, they would seem very robotic. We found, though, that as long as they had some emotional content, you could tell if they were upset or flirtatious or relaxed, that players would very smoothly kind of imagine the words and fill in the stories much more effectively than we could simulate in the computer. So as game designers, we in fact kind of decide a lot of the aspects of the simulator we're going to offload to the imagination, you know, for that very reason. Yeah.
Community is obviously a big facet of the Web 2.0 philosophy, and I was curious as to whether you had any thoughts or observations around bootstrapping specifically. Often that's going to make or break a lot of these different technologies.
Yeah, I've actually done a lot of measurement on that. When The Sims came out, I was really surprised by how large and diverse that community was, and I went back and I started doing a lot of measurements of it and studying how it grew. And it was very interesting because it has very much kind of a pyramid structure, almost like an ecological pyramid, where you have a very casual set of people at the bottom supporting a larger set of people browsing above that and telling stories with the Sims. Above that, you have, you know, a smaller number of people building websites for hosting content, and then you have people actually making content above that, and then actually people creating custom tools for the content creators. Every level, in some sense, is enabling the level above it. The level above it is getting payment through recognition from the level below it. But they tend to grow from the bottom. So first you get a certain number of casual users. There's some critical mass at which you now start expanding the next level of browsers or storytellers, and the next level. And there are different reasons that cause somebody to promote from one role to the next. What was really interesting to me was that in a lot of these communities, we had people that were spending a huge amount of time building cool, you know, costumes or objects for the Sims, putting it on websites, but they would never play the game. They had, you know, been done with the game for months. For them, the game was the community and building stuff and being the most famous artist in this community. So they had actually, in some sense, graduated the game itself, and the community was now the game and the role they were filling. So I've spent a lot of time actually also looking at older game communities and the way in which the shape of that pyramid can kind of taper off or change shape. I've seen pyramids actually clip off at the bottom and go off in their own little bubble universes. One example of that was the Quake community, where when Quake first came out, of course, you had a lot of hardcore players going in and playing, you know. A few people started realizing that they could use it for machinima, and so they started building cool machinima tools and were doing weird things with Quake. It still existed, but they never played Quake per se. Quake was now a movie-making tool for them. So I've seen a lot of different kind of trajectories for these communities. Sure. Yeah.
You spoke about, first of all, it was a very stimulating talk, as always. Thank you very much. One of the things that you spoke about was the emergent properties in systems as you move up levels of abstraction. Can you talk a little bit about anticipating some of those emergent properties, and what are the opportunities and the risks for a designer with respect to those emergent properties in systems?
Well, because they're emergent, they're notoriously difficult to predict. In general, what seems to happen at every level of emergence is that you're widening the possibility space for what that system can achieve, and that's really the reason that's driving, the jump in complexity, is the fact that by jumping in complexity, having these specialized agents basically cooperating as a unit, they now enable a much larger behavioral kind of possibility space, which allows them to more effectively discover a higher fitness strategy. So I'd say, in very broad terms, the most specific thing you can say is that you're enabling a broader set of possibilities at every level. Which is why biology seems so much more diverse and interesting than physics, let's say. But beyond that, it depends a lot on the system you're talking about.
It seems like at some point, some of those systems, when they make that step, they break down entirely, and other ones generate new possibilities.
Well, I think there's going to be a dynamic process at every level, and so that more complex system, emergent system, has to be at a higher competitive advantage than the one underneath it. If there's a really simple way to solve the same problem, then that higher order system is not going to be able to be an advantage at all. And we still see that these higher order systems do not necessarily displace the lower level ones. I mean, we still have prokaryotes on the Earth, incredibly successful as organisms, despite the fact that we have large invertebrates. So the invertebrates are just filling a different niche that did not exist before the prokaryotes. And in some sense, the invertebrates are much more dependent upon the prokaryotes than the other way around. So almost like the community pyramid, these levels above are really dependent upon the lower levels of organization that become their infrastructure.
For something like SimCity, do you have any evidence that's come back to you about people actually gaining an understanding of how cities work, like maybe professional city managers writing you and saying, hey, I played this, I got a new insight?
I've had a lot of people tell me that anecdotally. It's almost, for me, more of a perceptual awareness thing. These things are notoriously kind of hard to measure, which is one of the reasons why I think things like simulations have not been adopted more in standardized education, because they're so dependent on standardized testing. But I've heard so many stories where, a parent was driving around with their 9-year-old, and the 9-year-old said, "Oh, why'd they put the industrial zone there? They should have put it over here." And the fact that a 9-year-old would have awareness of their environment to that level surprises a lot of people. It doesn't surprise me at all. One thing I think that's lost on a lot of people is that if you look at a kid playing a game and the way they approach it, they automatically, instinctively, somehow trip over the scientific method. They'll sit there and just start pressing buttons, observe what happens, think about it. Oh, maybe it works this way. They'll eventually, very quickly, build a model in their head, a hypothesis of the way it works. They'll confirm it through experimentation, and then continually elaborate and refine that model through more and more experimentation. And that, in some sense, is probably the most valuable thing you could ever learn, is how to approach any complex system and develop an intuition for what the underlying model for it is, or at least an effective model that you can use to predict and understand it, which is true of almost any game whatsoever. I think that there are a lot of people now trying to take games specifically to teach specific types of content, and I think they're great for that as well. But I think it's almost more that kind of inherent interactivity, building a model of the system that you're presented with, that is the basis of almost every game. Yeah?
Do you either personally or have any plans to apply this to economic modeling, say sim stockbroker type thing? Seriously, I mean, SimAnt, a lot of the things you described.
Yeah. Well, in some sense, SimCity is a very economic model. One of the things that I found from a game design point of view, one of the things I found from a game design point of view, not necessarily from an educational point of view, is that games are more satisfying when the player has a really clear sense of what their contribution to the system was. I did a game a while back called Sim Earth, which is a fairly elaborate model of global dynamics, climate, including things like ecosystems, continental drift, and all this stuff. Because it was a fairly realistic model, when the player went in and did something, I might build an entire mountain or continent, but over few hundred million years, continental drift is going to erase it, or evolutionary, it could extinct the species, but then everything else evolves around it. And then it's really hard to go back and say, okay, what effect, now the planet's in an ice age, did I cause it or not? It was such a complex causal chain of, multi-threaded systems that the player had no sense whatsoever of, did I cause that or not? Which led me to spend kind of more time in systems where players had pretty obvious credit assignment for what they've done. In the game I'm working on now, Spore, we put the player in a very central design role at every level and made that very central to the way the simulation works. So when the simulation is pushing back, it's pretty clearly based upon the fitness of what you've designed or what you've built. Relative to a system where you're in this giant stream with a million things going on, if I throw something in the stream, I have no idea, if I influenced it or not. So economics tends to be somewhat more in that category. I'm not against, I think economic systems, if they could be visualized. In fact, that adaptive landscape I was showing you, we did a lot of models using that as a metaphor for economics, where basically it's a profit landscape, and you actually have companies now hill climbing on that profit landscape. Yeah, so I've actually used that a lot, in terms of economics. It's really useful as kind of a metaphor. Yeah.
Speaking of Spore, do you know when we can expect that?
Real soon now. It's kind of in the last stages. It's going to come out sometime not too late next year. Not too late of next year. Actually, first half, hopefully. But it's it's one of those things that you don't want to screw up. I've spent like so many years of my life working on it that I don't want to rush it out for a few months here and there at this point. But yeah, I'm looking forward to it. Yeah.
So you've had a lot of luck building games that appeal way beyond the hardcore to a very broad audience. Do you have any thoughts on how you build a team and how you build a design process to actually build something that appeals to such a big audience?
Yeah, actually a lot of thoughts. One of the things that we've been lucky about is I've always been able to attract a larger number of females on my teams than most game teams normally have. And that's kind of a chicken and egg thing when they, if there are any females that happen to want to work in the game industry, I don't know what they'd want to, but they look around and they say, what kind of games would I like to play? And they initially would look at SimCity and say, oh, I'd rather work for SimCity than, Postal or whatever the games are. And then, we got designers in those roles, producers, etc. And in some sense, a lot of very casual people that were interested in games that gave a very different kind of design philosophy infused the next set of games. And so my Sims team was about 40% female, and the sport team is pretty heavily female as well. So I think that's one good starting point, and that has more to do with the gender balance issue. But automatically, I think I don't think it's that women want women games or pink games or anything like that. They want good games. I think women, if anything, are more discriminating about how they spend their entertainment time than men are. Men will do the stupidest thing for entertainment, but in some sense that leverages itself out to in the broader demographics as well. So you'll appeal to older people as well as younger people. I think in general. Yeah.
From a game design perspective, if you want to take advantage of this emergence theory, you need a sort of Darwinian environment almost. So, given that in games your fitness criteria is how fun is the game, how do you if I wanted to emergently create video games?
Yeah, I know exactly what you're saying, and the answer is sharp interns and prototypes. I spent a lot of time trying to get really sharp interns in, and the first role I always put an intern in is prototyping. And maybe it's, a prototyping a couple of years ahead of my next idea or specific components of the thing we're working on now. But it's really good for them. They can do these tasks in a few weeks, or a month or so. It's a very quick turnaround where you play the prototype and say, hey, it's kind of fun. Let's try this and try that. In some sense, it's kind of like cooking. You don't know what it's going to taste like until you put all the ingredients in. But you want to try it. You don't want to cook a whole, for an army of 100 until you've tried out a little bit of the recipe first. And so prototyping really is a whole different skill set that, and that's what I was kind of talking about with the exploring that dynamic space where we build, like for Spore, I lost count, but I know we built well over 200 prototypes. Individual playable prototypes for very specific elements of the game. And, 120 of those prototypes sucked. They really did. But they saved us huge amounts of money because we knew not to develop that, the game in that direction. It was basically the giant tree that we were pruning the branches as cheaply as possible, leaving us with maybe 20% of the trees on the branch that we can now invest a little bit more in exploring, with a higher probability of success. But so far, and that's still not being able to look down at the entire tree, at a map of it, and figuring out what should be there. It's still a kind of a blind search, but it's a blind search at the least possible cost. Yeah?
What's your thoughts on the current state of the game industry and kind of the fact that a lot of smaller independent developers are being eaten up by bigger publishers, and just innovation in general seems to be really kind of a thing of the past, with few exceptions?
I've kind of heard that come and go. I mean, I think it's probably more true now than it had been in the past, because primarily the cost of creating a new AAA title is so high. I think the next generation systems kind of caught everybody off guard. That's one of the reasons why I'm kind of I'm actually spending more than I probably should investigating procedural systems right now, because I see that as like the only kind of really clear path for us to produce really interesting, emergent, large, experienced worlds without throwing 300 people at it. I think at the end of the day, I want the computer to be doing more and more of the game design, or the player communities, because every time we've given the players tools to make things, they've always exceeded our expectations. Now you're dealing with the problem of, okay, the players are creating 90% crap and 10% is pretty good. How can we make the tools better so that 50% of what the players are creating is good, instead of 10%? And I, would rather put that on the tool load than the player. I mean, you can say, these players aren't talented, but really, it's our tools are bad, is I think the more fundamental problem. So long term, I'm kind of committing myself to going down the path of giving the players more high leverage tools, because they enjoy making stuff and they really enjoy spreading it and sharing it once they've made it. Now we just need to make that a central part of our game design. So basically we need to co-opt our players to become our game designers for us. So I think that that's about the best path I can see. There are probably a lot of other approaches, but yeah.
One thing about most computer games and console games today is that they tend to come with these 40 or 50-page manuals. And so I guess two questions. One is Spore going to have one of these enormous manuals? But more importantly, as the game designer, what's your take on this? Do you expect them to be able to play the game in its entirety just by starting it off and clicking it around, or do you expect them to read the first 20%? Or what?
Yeah, I mean, right now our kind of assumption is the players will not read the manuals. And so every time we do playtesting or anything like that, we don't tell the players hardly anything. And we're trying to figure out, ideally you want the player to be able to sit down. It should be a fun process to learn. Now, you don't have to read a manual to go watch The Sopranos, And for a lot of people, that's kind of an alien concept, that you have to read a manual before you enjoy this entertainment experience. And I think if we need to hit, a wider group of people, which we do need to hit, you can show somebody how to use the web in about 2 minutes, and then they can pretty much learn the rest on their own. I think games should be the same way. I think, any learning should be embedded in the game as an enjoyable process. On the other hand, I do like the idea of a really nice manual, but more as almost a reference, a motivational reference, that if you're interested in this thing, you can open the manual. It'll tell you a little bit more about evolution or earth science or whatever. So I think of the manuals really as, and in general, in education, I think that computers and games are probably the most suited not for educating somebody about a subject, but for motivating somebody. I found that to be by far and away the most powerful use of computers in education, is getting somebody really excited about a subject that otherwise they would think is dry and boring, at which point they have endless opportunities to go out and explore that. If you get a kid motivated about a subject, try to stop them from learning about it and see what happens. They'll find a way to learn it. So I'm much more interested in designing a game that would make the player then want to read the manual, rather than designing a game where you have to read the manual first to play the game. Yeah?
How do you feel about graphics as far as they affect the ability to really engage in something like a game or a simulation, make it real for people? I mean, obviously graphics have come a long way since you started making simulations. How important are those to Spore and other things like that?
I think graphics are really interesting. It's one of those technologies that in some sense I think we've gotten pulled a little bit aside. We've got a little distracted by as an industry on. If I go back and play some of these really old games where I have these little 5-pixel characters that are super low res, it was amazing how engaged I was with those characters. It was amazing how much my imagination glossed over the fact that the graphics sucked, but the character seemed real because of what it was doing or because of its context in the game. In some sense, when I play the really modern, interesting games nowadays, the graphics are not the weak link at all. The weak link is things like the physics and the AI. When everything I shoot with my gun, only the window breaks and everything else is fine somehow, or the characters go up and they repeat the same line of dialogue over and over and over. Now we have basically the graphics up to here, and the AI is still down there. The physics are down here. So I would easily give up half the graphics we've got to bring those other things more in line with it. Because a game like Grand Theft Auto, which I loved, at the time when it was released, didn't really have state-of-the-art graphics, but it had reasonable graphics, and it had reasonable AI, and it had reasonable physics, and really it was the balance of those things that made it an interesting dynamic world. Had it had better graphics at the expense of the other two, the game would have sucked. So I'd almost rather see more emphasis on these other things. In the back.
So a different genre, like I don't know, first-person shooters, Half-Life 2 is a game I'm thinking of. Whenever I read a review, they talk about open-endedness.
Yeah.
These games have struggled to be open-ended for many, many years. Now people use the term interactive fiction. But if you really lay it out, I mean, games like Half-Life 2 really come down to this long, long path that you walk down. And if you and I play the game, our gaming experience will be pretty much the same, and nothing that we will encounter has not been foreseen by the creator of the game.
Yeah.
I just went back to and read about Deadline, an Infocom adventure from 1982, and the article talked about how there was a bug in the system, but the system stayed consistent through the bug and actually generated some interesting behavior that obviously the creator of the game had not foreseen. Do you see any of the insights that you've gotten from your whole sim experience could propagate into this genre to kind of, instead of just basically designing an interactive movie, instead of going to the theater and playing through this game, that you just put in a bunch of components and somehow generate emergent behavior as you've done it in this space, but kind of port that type of experience into this world of first-person shooting, interactive fiction?
Yeah, in fact, I agree. Half-Life, especially Half-Life 2, feels like it's very much like on rails in the way they direct the player experience, which is why I always prefer to game like Battlefield 42, which in fact has these kind of simple elements that you can recombine in really interesting ways. In Battlefield 42 and some of the other versions of it, players, aside from playing the game, would get together and do these weird exploits where they were looking for strange things they could exploit within the physics engine, and it became a team sport. Can I jump out of a tree while you're flying an airplane by and land in your cockpit? And they would end up doing these performances, these amazing performances. It was like watching the ballet, and it would involve several players, almost like in a sporting way, working together as a team, and then they would have 20 other people sitting there watching as their audience. And so I have seen systems like that and because of that, you're not just kind of giving them a game, but you're giving them a system, and they can kind of decide what to do with it. I thought it was very impressive watching the evolution of Quake into a machinima tool, kind of for the same way. But Quake itself was, extremely kind of linear.
It seems like the quality expectations are so high that if you put a title out like Half-Life 2, that you expect every single shot from it to be perfect.
Yeah.
Right? And I think what you're saying is this emergent behavior will be 80% cool, 20% weird and crazy and funny, and may break some people's experience with the game.
Yeah.
It seems like right now people are not willing to take that. If you actually open up, you might actually break persona with the people in this. If everything's not completely scripted.
An interesting metric, kind of for what you're describing, is how interesting are the player stories. When we, nobody ever says how great this cutscene was in this game. They don't go tell everybody how excited this cutscene was that they saw. But when they do something really weird and unexpected in the game, they'll tell a story, post it on the web, whatever. When the Sims first came out, a lot of hardcore gamers assumed it was an adventure game because it was about people. Every game about people up to that point had been a very scripted, linear adventure game. It was only after the first few people started playing it and started posting these stories of, you wouldn't believe what happened. This fire started over here, and he ran over here, but then this happened, and they would describe these really interesting, and every player story was totally different. And they were able to infer the fact that it was an open-ended simulation by the diversity of player stories. Whereas if you had 10 Half-Life players tell you their story, it'd be the identical story. And so you, in some sense, get a really good instinct for the possibility space of a game by how diverse the player stories are. So I think, and that in fact is really attracting a very different type of player, that sees these things as more as creative endeavors and not so much, a puzzle, can I solve the puzzle or not? And I think, those games the open-ended games are hitting a wider group of people. Yeah.
So, without requiring everyone in the room to have to sign an NDA to answer this question, what directions are you thinking of after Spore comes out, if you're even thinking that far ahead for what areas you might want to look into in gaming space?
Just in broad terms, I'm really interested in using games to get people involved in real-world issues, because I think games are incredibly motivational, if done the right way. I think that it's amazing how much of what's going on in the world people are either voluntarily or involuntarily unaware of. that we could use games to basically just give the average person a much wider awareness of, current events and the way the world is currently working or not working. So kind of, or social, things with a more social agenda, but in a soft, entertaining way. So, again, not beating them over the head, come do this, it's good for you, but finding a way to make that feel like an entertaining experience where you're co-opting their natural passions into that smoothly. So I know it's abstract, but yeah.
Actually, along a similar line, sort of you can get this open-ended gameplay, and you can also do these very sort of on-rails linear things. The sort of on-rails linear storytelling, however, almost replicates some of our previous mythology in terms of what stories everyone knows because they played through this game, and in a way can also focus a player experience in a much more narrow way than this sort of playpen style game. Do you think that your games suffer from this lack of focus in terms of bringing these issues to life?
No, I think of stories and play as fundamentally different things. I think they're both technologies for us to build models of the world. I think stories are very important. I think stories do exist in a very strong form in games, but I think that they're all player stories. I think what we need to do is understand what's the story that the player is playing out, and how do we basically amplify that? How can we make the computer aware of that I'm trying to do a murder mystery or a comedy or whatever, and then change the soundtrack, change the elements, change the way the AIs react to me, as opposed to us kind of slightly imposing a story on them and giving them the illusion of free will, but not really because they'll get too far off the story path. I mean, I think that's the worst of both worlds, really. So I would much rather, maybe give them a backstory, but then say, at this point, the story is entirely up to you, and I can replay Hamlet, or I can turn it into Die Hard, depending on what I do. But really, it's the player driving the story from that point forward. So I think the player stories, to me, have always been the most fascinating ones, and the ones that I wish I could teach the computer to recognize more effectively. Yeah.
What's come out recently that you like play a lot? Like recommendations?
Oh, games?
Yeah. What's really
Oh, God. Probably nothing that really grabbed me recently. Actually, there was a game Thrillville on the Xbox 360 that was a surprisingly good version of Roller Coaster Tycoon or Theme Park. I was just amazed that the building interface was amazingly well done on that, I thought. But I haven't really had time to play a lot of games, being so heads down in spore as I would like to. I've been playing a lot of games on my DS. I think the DS has got some of the most innovative games out there right now. Okay. Let's see. Anybody? Yeah.
So I'm wondering, there's a whole generation of baby boomers are getting old now, and they're going to have a lot of leisure time. And specifically wondering what I should get my dad for Christmas.
Well, at the risk of offending Microsoft, I would say a Wii. But apparently a lot of senior citizen homes have Wii bowling leagues now. Because, it's a game they understand, they're familiar with, they know the rules, and you roughly kind of go up and do it the same way, and they're too weak to hold a bowling ball. So apparently all these, old people are playing Wii bowling. But I don't know, it probably depends a lot on kind of what his interests are. I think there are a lot of, still really good PC strategy games that somebody who's interested in history, it's amazing how fun turn-based games still are to me. Which you would have thought turn-based games would be this old art form, but Sid Meier almost single-handedly kind of rescued that art form and carried it forward. So maybe even something like Civ, maybe even one of the older versions of Civ. Yeah, by the post.
Yeah, in terms of human evolution, a lot of human behavior likes to use stories to convey information about complex events. Mm-hmm. And it seems like the games that you develop are a series of complex events, and people kind of tell themselves stories of why certain things happen. And I was wondering, for your personal experience, what kind of stories do you see people telling themselves about the games they play?
Well, stories really, any story is a set of causal events that are linked together that has some dramatic outcome. The reason why storytelling, like we see in movies, I don't think can ever be accomplished in games, is because the director understands what's going to happen in the future. The director understands that this minor little event of this thing falling off the table is going to cause this guy to miss his contact and the world to end or whatever. And only with that knowledge of the future, of what that full causal chain is, do you know where to put the camera and how to basically, dramatically frame that causal linkage. Now, if the player is actually controlling what's going on, and in fact you really have free will, you can't know what the future is going to be. You don't know what that causal chain is in advance. So I think that's the fundamental difference between what I think of as kind of linear storytelling and play. I think what we can do, though, is the computer can look at the past causal chain that the player's traversed, use that as a guide for at least thematically framing, amplifying, and enforcing events into the future. So that if I go around acting in a certain way in a game, the computer will decide it's a romance, and it'll change the music, and the lighting will get low. If I act a different way, it'll decide it's a horror thing, and all of a sudden a storm starts, and the music gets spooky, and the camera gets behind me. We can change the presentation of what's going forward based upon the causal chain in the past. But I don't think we ever want to basically have the causal chain preset and now have to force the player to stay on it. At which point you have, again, the worst of both worlds. Yeah, pretty much. And the combinatorics of that just don't work, obviously. So I guess I should stop now. Thanks, everybody.